The world is finally quiet, and I'm so happy you're here. You found Science Blanket, and tonight, we are wrapping ourselves in a story of incredible transformation. Have you ever considered that something as simple as the carbon in a pencil could be pressed by the weight of 100 miles of Earth until it becomes the hardest, most brilliant material in existence? Tonight, we're exploring the silent, ancient world of diamonds. These aren't just sparkling gems, they are time travelers. Some of the stones we'll talk about tonight are over 3 billion years old, meaning they were already ancient before the first dinosaur ever walked the Earth. We're drifting deep into the mantle, where extreme heat and crushing pressure create a perfect, rigid lattice of light, a stone so invincible that only another of its kind can even leave a mark on it. As we begin, imagine yourself descending into the heart of the Earth, not into darkness, but into a place where the very rocks glow with a deep, pressurized heat. You don't need to worry about the chemistry of the carbon lattice or the math of the refractive index tonight. Just let the weight of 3 billion years of history tuck you in. If this blanket of deep time and light helps you find peace, I'd love for you to subscribe and join our community of sleepy explorers. It helps us keep the stories flowing for everyone searching for a quiet place to land. Now, let's take a slow, deep breath together. As you exhale, imagine that same pressure that creates a diamond is now just a heavy, warm blanket pressing you safely into your bed. Release the tension in your jaw, let your shoulders melt into the mattress, and feel your mind become as clear and still as a polished stone. You are safe, you are supported, and the world can wait until morning. Let's explore the sparkling mysteries of the diamond together. Deep beneath your feet, far below the deepest ocean trenches and the foundations of ancient mountains, lies a world of unimaginable pressure and searing heat. It's in this hidden realm, somewhere between 90 and 150 miles below the Earth's surface, that one of nature's most extraordinary transformations takes place. Here, in the mantle of our planet, carbon atoms are forced together under conditions so extreme that they arrange themselves into something remarkable. These atoms don't scatter randomly or form loose connections. Instead, they lock into a precise geometric pattern, a rigid structure known as the diamond cubic crystal lattice. Each carbon atom bonds with 4 others in a 3-dimensional framework of perfect symmetry, creating the hardest naturally occurring substance we know. The recipe for making a diamond sounds deceptively simple. Take carbon, apply tremendous pressure, add intense heat, and wait. But the reality is far more complex and fascinating. The pressure required is almost beyond comprehension, thousands of times greater than what we experience at sea level. The temperature must reach levels that would instantly vaporize most materials at the surface. Under these conditions, carbon atoms are squeezed so tightly together that they have no choice but to bond in that distinctive crystalline structure. It's a process that seems almost alchemical, transforming one of the most common elements on Earth into one of its rarest treasures. Time, in the world of diamond formation, becomes almost meaningless. Some diamonds crystallize in a matter of hours, rapid by geological standards yet still requiring conditions we can barely recreate in our most advanced laboratories. Others take an incomprehensibly long journey through time, forming over billions of years as carbon atoms slowly, methodically arrange themselves into their crystalline prison. The diamonds that eventually make their way to the surface carry with them the history of our planet. Scientists have determined that natural diamonds range in age from 1 billion to 3.5 billion years old. Think about that for a moment. Some of the diamonds we see today began forming when Earth itself was still young, when the first stirrings of life were just beginning in ancient oceans, or perhaps even before life existed at all. These ancient crystals hold secrets from eras we can barely imagine. A diamond that formed 3 billion years ago witnessed the rise and fall of entire continents, the assembly and breakup of supercontinents, the evolution of life from single cells to the complexity we see today. Locked within that rigid lattice of carbon atoms are tiny impurities and imperfections that tell stories about the conditions deep within Earth's mantle billions of years ago. Scientists can read these diamonds like time capsules, extracting information about temperatures, pressures, and chemical compositions that existed in places and times we could never otherwise access. But here's something remarkable that few people know. The diamonds we treasure, the ones we set in rings and necklaces, the ones we use in industrial applications, aren't actually stable at Earth's surface. They're what scientists call metastable, meaning they exist in a form that isn't quite in equilibrium with their environment. Given enough time, truly immense amounts of time, diamonds will slowly convert back to graphite, the soft gray material in pencil lead. Both diamond and graphite are pure carbon, but their atoms are arranged completely differently. At surface temperatures and pressures, graphite is actually the stable form. So in a sense, every diamond is slowly, imperceptibly transforming back into something far more ordinary. But you needn't worry about your jewelry turning into pencil lead. This conversion happens on timescales that make even geological time seem brief. We're talking about periods so long that the sun will likely die before your diamond shows any sign of change. The question then becomes, how do these diamonds, formed in the crushing depths of the mantle, ever reach the surface where we can find them? They certainly can't walk. For billions of years, diamonds remain trapped in their subterranean prison, locked away in darkness and pressure. Their journey to the surface requires a catalyst, a violent event powerful enough to transport material from depths of 100 miles or more up through the crust and into the light. That catalyst comes in the form of volcanic eruptions, but not the kind you might picture when you think of a volcano. These are extraordinary explosions, driven by unique types of magma that originate deep enough to reach diamond-bearing rocks. This magma travels through what geologists call kimberlite and lamproite pipes, narrow conduits that punch through the Earth's crust like geological elevators. The eruptions that create these pipes are incredibly rapid and violent. The magma rises so quickly that diamonds don't have time to convert back into graphite or to be destroyed by the heat. They're simply carried along, passengers in a torrent of molten rock racing toward the surface. When the eruption ends, the pipe cools and solidifies, leaving behind a vertical column of kimberlite or lamproite rock peppered with diamonds. These pipes are rare, scattered across the planet like winning lottery tickets. Finding them requires both geological knowledge and considerable luck. We humans, for all our technological prowess, have barely scratched the surface of our own planet. The deepest hole ever drilled, the Kola Super Deep Borehole in Russia, reached just over 7 miles down. That's an impressive engineering feat, a triumph of human determination and ingenuity. But it's only a fraction of the distance to where diamonds form. We've sent robots to Mars, placed telescopes in orbit that can see the edge of the observable universe, but the interior of our own planet remains largely inaccessible. The conditions down there, the pressure and temperature, destroy conventional drilling equipment. So we remain dependent on those volcanic pipes, on nature's own delivery system, for nearly all the diamonds that make their way into human hands. Yet not all diamonds travel directly from pipe to pocket. Over millions of years, The forces of erosion go to work on kimberlite pipes exposed at the surface. Wind and rain and ice slowly break down the rock, liberating the diamonds trapped within. Rivers carry them away, tumbling them along riverbeds, sorting them by weight and size through the patient work of flowing water. These are called alluvial diamonds, and they can travel remarkable distances from their original source. A diamond that formed beneath Africa might end up in a riverbed hundreds of miles away, mixed with sand and gravel, waiting to catch the eye of a prospector panning for treasure. Throughout history, some of the world's most famous diamonds were discovered in alluvial deposits, found by people who had no idea where these stones originally came from. And then there are the diamonds that come from beyond our world entirely. Scientists have discovered diamonds inside meteorites, crystalline structures formed not in Earth's mantle but in the depths of space. Some of these diamonds may have formed in the aftermath of stellar explosions, in the final violent moments of dying stars. Others might have crystallized in the collisions between asteroids, brief moments of extreme pressure and temperature not unlike the conditions in Earth's mantle. These extraterrestrial diamonds remind us that the processes that create these remarkable structures aren't unique to our planet. Wherever carbon exists under the right conditions of pressure and heat, whether in Earth's mantle or in the cold darkness between stars, diamonds can form, each one a testament to the fundamental forces that shape matter throughout the universe. When mineralogists needed a way to classify the hardness of various substances, they developed what's known as the Mohs hardness scale, a ranking system that runs from 1 to 10. At the very top of this scale, standing alone in its supremacy, is diamond. A rating of 10 on the Mohs scale means that diamond is the hardest naturally occurring material on Earth. Nothing else in nature can scratch its surface. If you take a piece of corundum, which includes rubies and sapphires and ranks 9 on the scale, and try to scratch a diamond, the corundum will simply skate across the diamond surface, leaving no mark whatsoever. Steel, which seems so hard and durable in our everyday experience, ranks only around 5 or 6. It can't even make a dent in a diamond's crystalline perfection. This leads to an interesting situation. If diamonds are the hardest natural material, and nothing else can scratch them, then only a diamond can scratch another diamond. This fact has been known for centuries and has shaped the entire diamond cutting and polishing industry. To shape a rough diamond into the brilliant gems we recognize, craftsmen must use diamond dust or diamond-tipped tools. They essentially use diamond to cut diamond, a practice that requires immense skill and patience. The process can take days or even weeks for a single stone, as workers carefully grind away material atom by atom, revealing the geometric facets that will eventually catch and reflect light in that characteristic sparkle. But here's something that surprises many people. Despite being the hardest material in nature, diamonds are not indestructible. They possess a property called cleavage, which refers to the tendency of a crystal to break along specific planes determined by its atomic structure. If you strike a diamond at precisely the right angle, along one of these cleavage planes, it will split cleanly in two. This isn't a flaw or weakness in the traditional sense. It's simply a consequence of the diamond's crystal structure, the same geometric arrangement that gives it such remarkable hardness. Expert diamond cutters actually use this property to their advantage, carefully studying a rough diamond's internal structure and sometimes cleaving it to remove flawed sections or to create multiple gems from a single large stone. But it also means that despite their legendary hardness, diamonds can shatter if struck the wrong way. A hammer blow in just the right spot can split $1 million diamond as easily as it might crack a walnut. The properties of diamonds extend far beyond their hardness, into realms that seem almost contradictory. Take heat, for instance. Diamonds conduct heat better than any other natural material known to science. Touch a diamond to your lips, and it will feel noticeably cool, even at room temperature. This happens because the diamond conducts heat away from your skin so efficiently that it creates a sensation of coldness. This thermal conductivity is so exceptional that jewelers sometimes use it as a test to distinguish real diamonds from imitations. A diamond will disperse heat so rapidly that if you breathe on it, the fog from your breath will disappear almost instantly. Glass or cubic zirconia, common diamond simulants, will stay fogged for several seconds because they can't conduct heat nearly as efficiently. Yet in a curious twist, while diamonds excel at conducting heat, they're remarkably poor at conducting electricity. Most materials that conduct heat well also conduct electricity well. Metals like copper and silver, for instance, are excellent conductors of both. But diamonds break this pattern. The same rigid lattice structure that makes them so hard and such efficient heat conductors also locks their electrons firmly in place. Those electrons can't move freely through the material to carry an electrical current. In their pure form, diamonds are actually insulators. However, and nature loves exceptions to its own rules, if certain impurities are introduced into a diamond structure, particularly boron atoms, the diamond can become a semiconductor. This has led to fascinating research into using diamonds in electronics, creating components that could theoretically operate at much higher temperatures than conventional silicon-based devices. Sound, that invisible phenomenon of vibrating air molecules, behaves in extraordinary ways when it encounters diamond. Diamonds conduct sound faster than any known substance. When a sound wave enters a diamond, it races through the crystal lattice at speeds approaching 12,000 meters per second, nearly twice as fast as sound travels through steel. This happens because sound waves are essentially vibrations passing from atom to atom, and in diamond's rigid structure, those atoms are held so tightly and uniformly that vibrations can propagate with almost no resistance. Scientists have explored using this property in acoustic devices and sensors, though the cost of diamond generally limits such applications to specialized equipment. The chemical stability of diamonds is equally impressive. They resist attack from virtually any acid. You could drop a diamond into concentrated sulfuric acid, into hydrochloric acid, into substances that would dissolve most other materials, and the diamond would emerge unharmed. The strong carbon-carbon bonds in the diamond lattice simply cannot be broken by chemical reactions at normal temperatures. But introduce enough heat, and the situation changes dramatically. At very high temperatures, around 700 to 800 degrees Celsius in the presence of oxygen, diamonds will burn. Yes, burn. They're carbon, after all, and carbon combusts when heated sufficiently in air. The diamond doesn't melt into a puddle, though. Instead, it oxidizes, combining with oxygen to form carbon dioxide gas. Your priceless gem literally vanishes into thin air, leaving behind nothing but invisible gas and perhaps a small amount of ash if impurities were present. This brings us to another peculiar property. Under normal atmospheric pressure, if you heat a diamond to extreme temperatures in an environment without oxygen, it won't melt in the traditional sense. Instead, it sublimes or evaporates, transforming directly from solid to gas without passing through a liquid phase. To actually melt diamond, you would need to apply tremendous pressure, millions of times normal atmospheric pressure, and heat it to temperatures exceeding 4,000 degrees Celsius. Under those conditions, diamond finally consents to become liquid. These are not conditions easily achieved in a laboratory, and they certainly don't occur anywhere on Earth's surface naturally. It's yet another reminder of just how extraordinary these crystals are, how they defy our everyday intuitions about how matter should behave. Even the way diamonds respond to temperature changes reveals the elegance of their structure. When heated, diamonds expand slightly, a property shared by most materials. But the amount and manner of this expansion is directly related to that diamond cubic crystal lattice, that perfect three-dimensional framework of carbon atoms. As thermal energy increases, the atoms vibrate more vigorously, and the average distance between them increases slightly. The lattice maintains its structure but grows minutely larger. Engineers who work with diamonds in precision applications, from cutting tools to optical devices, must account for this thermal expansion to ensure that components function correctly across a range of temperatures. Perhaps the most visually apparent property of diamonds, the one that has made them objects of desire for millennia, is their interaction with light. When light enters a diamond, it encounters a material with an exceptionally high refractive index, a measure of how much the material bends light as it passes through. Diamond's refractive index is around 2.4, meaning light slows down and bends significantly as it enters the crystal. This high refractive index is what gives diamonds their exceptional brilliance, that intense sparkle when light bounces around inside the stone and reflects back out toward your eye. But there's more to a diamond's beauty than just brightness. Diamonds also exhibit what gemologists call fire, the flashes of spectral color that seem to dance within a well-cut stone. This happens because diamond doesn't just bend light, it disperses it, splitting white light into its component colors like a prism. Different wavelengths of light bend by different amounts as they pass through the diamond, separating into reds and blues and yellows and greens. A skilled cutter positions facets to maximize this effect, creating a gem that seems to contain rainbows within its crystalline depths. The combination of brilliance and fire, both consequences of diamonds' unique optical properties, has captivated humans for thousands of years and continues to make diamonds among the most prized of all gemstones. The magic of a diamond sparkle isn't simply about light passing through the stone. It's about light becoming trapped, bouncing repeatedly off the internal surfaces in a phenomenon physicists call total internal reflection. When light traveling through diamond hits the boundary between the diamond and air at a shallow enough angle, it doesn't exit the stone. Instead, it reflects completely back into the diamond, as perfectly as if it had struck a mirror. This light then travels to another internal surface, reflects again, and continues this dance inside the crystal. Eventually, some of these light rays find their way out through the top of the diamond, the table and crown facets, emerging as brilliant flashes that reach your eye. But this only happens efficiently when the angles are just right, when the geometry of the cut creates the conditions for total internal reflection to occur repeatedly before light finally escapes. This is why a diamond sparkle depends so heavily on precise cutting angles. A diamond cutter can't simply grind facets at random and hope for beauty. Every angle must be calculated to work with diamond's optical properties, particularly that high refractive index we discussed earlier. If the pavilion facets, those on the bottom half of the stone, are cut too shallow, light will pass straight through the bottom of the diamond and be lost. The stone will look lifeless, what jewelers call a fisheye appearance. If the pavilion is cut too deep, light will reflect at wrong angles and leak out the sides, again robbing the diamond of its brilliance. There's a narrow range of ideal proportions where everything works together, where light enters through the crown, reflects internally multiple times, and returns through the top in a dazzling display of brightness and fire. Finding these proportions requires not just craftsmanship but deep understanding of optics and geometry. The journey from rough diamond to finished gem is one of careful destruction. A rough diamond pulled from the earth might look nothing like the sparkling gem you'd recognize. It could be coated in other minerals, irregularly shaped, perhaps resembling a translucent pebble more than a jewel. To reveal the beauty within, cutters must remove enormous amounts of material. On average, a rough diamond loses about half its weight during cutting and polishing. Sometimes the loss is even greater, 60 or 70%, particularly if the rough stone has significant flaws that must be cut away. This waste represents not just lost material but lost value. Every grain of diamond dust that falls away during cutting represents money literally ground into powder. It's a necessary sacrifice, though. That remaining 50%, shaped into perfect geometric proportions with carefully angled facets, will be worth far more than the original rough stone, even though it weighs less. The cutter's skill lies in visualizing the ideal gem hidden within the rough crystal and removing everything that doesn't contribute to that vision. The art and science of diamond cutting has evolved over centuries. Venetians in the 14th century were among the first to perfect early diamond cutting techniques. Before this period, diamonds were appreciated largely in their natural form, perhaps with minor polishing but no systematic cutting. The Venetians discovered that by carefully grinding facets onto a diamond surface, they could dramatically enhance its beauty. They developed primitive cutting wheels and began experimenting with different shapes and configurations. Word of their technique spread, though they tried to keep the details secret, and Venice became the center of the diamond trade for a time. These early cutters worked without the benefit of modern optics or mathematical theory. They learned through trial and error, through careful observation of how light behaved in stones they'd already cut, gradually developing an intuitive understanding of principles that wouldn't be formally described by science for centuries. One of the earliest standardized diamond cuts was called the table cut. This relatively simple design featured a large flat top facet, the table, surrounded by a few other facets that sloped down to form a shallow pavilion. By modern standards, table cuts seem primitive. They don't maximize brilliance or fire the way contemporary cuts do. But in their time, they represented a significant advance over uncut or simply polished diamonds. The large table allowed light to enter the stone, and the angled facets below provided some reflection, creating a sparkle that seemed almost magical to people who had never seen such a thing before. Table cuts appeared on the jewelry of European nobility, on royal crowns and ceremonial objects. For several centuries, this was the height of diamond cutting sophistication. Modern diamond cuts bear little resemblance to those early attempts. Today's cuts maximize brilliance through mathematical proportions derived from careful study of diamonds' optical properties. The most popular modern cut, the round brilliant, features 57 or 58 facets arranged in precise geometric patterns. Every angle, every facet size and placement has been calculated to optimize the path of light through the stone. Computer models can now simulate how light will behave in a diamond of any given proportions, allowing cutters to plan their work with incredible precision. Other cuts, like the Princess, Emerald, Oval, and Marquise, each have their own optimal proportions, their own mathematical ideals. Some cutters spend years studying these geometries, learning not just to follow established patterns but to understand the underlying physics well enough to innovate, to design new cuts that might coax even more beauty from these remarkable crystals. Not all diamonds are created equal, even at the atomic level. Gemologists classify diamonds into different types based on the presence or absence of certain impurities. Type IA diamonds represent the pinnacle of purity. They contain almost no impurities, no nitrogen, no boron, nothing but carbon atoms in that perfect lattice arrangement. These diamonds are extremely rare, making up less than 2% of all natural diamonds. Because they lack impurities, Type IA diamonds tend to be exceptionally transparent, allowing light to pass through with minimal absorption. Many of the world's most famous diamonds, legendary stones with their own names and histories, are Type IA. They're the diamonds that come closest to the idealized image of what a diamond should be, though ironically, some small impurities can actually enhance a diamond's character, giving it subtle colors or other distinctive features that make it unique. The rarity of Type IA diamonds hints at a broader truth about diamond mining. Only about 30% of mined diamonds are gem quality, suitable for use in jewelry. The rest, the majority, have too many flaws, too much color, or other characteristics that make them unsuitable for ornamental purposes. This doesn't mean they're worthless, though. Far from it. More than 80% of all diamonds mined are used for industrial purposes. Diamond's hardness makes it ideal for cutting and grinding other materials. Diamond-tipped drill bits can bore through solid rock. Diamond saws can cut through concrete, ceramics, even other diamonds. Diamond grinding wheels are used to shape and finish metal parts in manufacturing. The aerospace industry uses diamond tools. Electronics manufacturing uses them. Medical device production uses them. In many industrial processes, nothing else will do. The cost of diamond tools is justified by their longevity and efficiency. They last longer than alternatives and can achieve tolerances and finishes that other materials simply cannot match. Even the waste from diamond cutting finds productive use. That diamond dust created when a gem cutter grinds facets onto a rough stone, along with the fragments and lower quality material that can't be used in jewelry or industrial tools, gets recycled into abrasives and other products. Fine diamond powder is mixed into polishing compounds used to create mirror-smooth finishes on metal, glass, and other materials. Some of this powder even finds its way into cosmetics, where it's added to creams and lotions, marketed as providing a subtle shimmer or supposed anti-aging benefits. The cosmetic claims are dubious, but the shimmer is real. Tiny diamond particles reflect light, creating a subtle glitter effect on skin. It's a curious endpoint for material that formed billions of years ago in Earth's mantle, carried to the surface by volcanic eruption, mined from the ground, cut away from a larger stone, and ultimately ending up as microscopic flecks in someone's face cream. Every part of every diamond eventually finds a use, a testament to how valuable this material is in all its forms, from the finest gem to the tiniest fragment. When most people picture a diamond, they imagine a colorless, transparent crystal, clear as ice and brilliant as starlight. But diamonds, in their infinite variety, occur in nearly every color imaginable. Delicate pinks and intense blues, vibrant yellows and mysterious greens, deep browns and even pure black. This rainbow of possibilities emerges not from the carbon atoms that form the diamond structure, but from impurities and defects within that structure. A perfectly pure diamond, one containing nothing but carbon atoms arranged in flawless geometric precision, would indeed be completely colorless. But perfection is rare in nature. Most diamonds contain trace amounts of other elements, atoms that infiltrated the crystal as it formed deep within the Earth. These foreign atoms, or sometimes missing atoms and other structural irregularities, interact with light in ways that create color. The most common colored diamonds are yellow, and their color comes from one of the universe's most abundant elements. Nitrogen impurities create yellow diamonds by replacing carbon atoms here and there throughout the crystal lattice. When light passes through the diamond, these nitrogen atoms absorb blue wavelengths from the spectrum, and what remains, what reaches your eye, is shifted toward yellow. The intensity of the yellow depends on how much nitrogen is present. A small amount might create just a faint tint, a barely perceptible warmth that could almost be mistaken for colorless. More nitrogen produces deeper, richer yellows, ranging from pale lemon to intense canary. These yellow diamonds are sometimes called Cape diamonds, named after the Cape of Good Hope region in South Africa where many were historically found. While they're the most common colored diamonds, that doesn't make them ordinary. A vivid yellow diamond can be spectacularly beautiful, holding sunshine within its facets. Blue diamonds arise from a different impurity entirely. Boron impurities create blue diamonds through a similar mechanism of selective light absorption. Boron atoms scattered through the crystal lattice absorb red, yellow, and green wavelengths, allowing blue light to pass through and reach the observer. The famous Hope diamond, perhaps the most celebrated gemstone in history, owes its striking blue color to boron. Blue diamonds are considerably rarer than yellow ones because boron is less likely to be present in diamond-forming environments. The concentration of boron needed is also quite specific. Too little and the diamond appears colorless. The right amount produces that coveted blue, ranging from pale sky blue to deep ocean blue depending on the precise boron content. Interestingly, because boron affects the diamond's electronic structure, blue diamonds can conduct electricity slightly, unlike their colorless counterparts. It's a small effect, but measurable, and it makes blue diamonds unique among gems. Green diamonds acquire their color through an entirely different process. Natural radiation exposure over geological time can produce green diamonds by altering the crystal structure near the surface. This radiation, typically from radioactive elements in surrounding rocks, knocks carbon atoms out of their positions in the lattice. These vacancies and displaced atoms create defects that absorb red and yellow light, leaving green to dominate what we see. The green color is often concentrated near the surface of the diamond because radiation doesn't penetrate deeply. Cut into the stone, and you might find that the green is only skin deep, with colorless diamond beneath. Some green diamonds, however, have been exposed to radiation throughout their entire structure, creating color all the way through. These are particularly prized. Natural green diamonds should not be confused with artificially irradiated diamonds, which can be created by exposing colorless stones to radiation in a laboratory. The natural process takes millions of years. The artificial process takes hours or days. Both create green diamonds, but collectors value natural color far more highly. Among all colored diamonds, red diamonds stand as the rarest. Not pink, though that's extremely rare too, but true red, the color of blood or rubies. Fewer than 30 genuine red diamonds are known to exist worldwide. Most are small, just a carat or two, and many reside in private collections or museums. The largest known red diamond, the Moussafe Red, weighs just over 5 carats, about the size of a small almond. The mechanism that creates red color in diamonds isn't fully understood, though scientists believe it relates to a particular type of structural deformation in the crystal lattice, a distortion that affects how light interacts with the carbon atoms. Whatever the cause, the result is breathtakingly rare. When a red diamond does appear on the market, it commands prices that dwarf those of colorless diamonds of similar size and quality. We're talking millions of dollars per carat, prices that reflect not just beauty but extraordinary scarcity. Black diamonds occupy their own category entirely. While colored diamonds get their hues from trace impurities or defects while maintaining their fundamental crystal structure, black diamonds are something different. They're polycrystalline, meaning they're not single crystals but aggregates of many tiny diamond crystals fused together. These are known as carbonado, a name derived from the Portuguese word for burnt or carbonized. Carbonado diamonds are opaque rather than transparent, with a porous structure that gives them a metallic luster quite unlike the brilliant sparkle of conventional diamonds. They're found primarily in Brazil and the Central African Republic, which is geographically puzzling. These two regions are separated by the Atlantic Ocean, yet they're the only significant sources of carbonado. This strange distribution has led to fascinating theories about their origin. Some scientists believe carbonado diamonds may have originated from asteroid impacts rather than forming in Earth's mantle like conventional diamonds. The theory suggests that either the diamonds formed in space, perhaps in a carbon-rich asteroid, and were delivered to Earth during impacts, or that the impacts themselves created the extreme conditions necessary for these unusual diamonds to form. The impact hypothesis would explain the unique structure of carbonado and potentially their puzzling geographic distribution, if both African and South American deposits relate to ancient impact events that occurred before these continents drifted apart. It's a controversial idea, not universally accepted, but it highlights how much mystery still surrounds these dark, enigmatic stones. Some carbonado samples contain minerals and isotopic signatures that seem consistent with an extraterrestrial origin, while others appear more Earth-like. The debate continues, and carbonado diamonds remain among the most scientifically intriguing varieties. Diamonds with strong, pure colors are called fancy-colored diamonds in the trade, and among these, the fancy vivid category represents the pinnacle. These are diamonds where the color is so intense, so saturated, that it dominates your perception of the stone. A fancy vivid yellow practically glows with golden light. A fancy vivid blue seems to contain the deepest ocean. A fancy vivid pink looks impossibly vibrant, a color that seems too intense to occur naturally. These fancy vivid colored diamonds are among the rarest gems in existence. While yellow diamonds are relatively common among colored diamonds, fancy vivid yellows are not. The vast majority of yellow diamonds show only faint or light color. To achieve vivid intensity requires just the right concentration of nitrogen atoms, distributed in just the right way. The same applies to other colors. Only 1 in a million diamonds shows strong natural color, and only a fraction of those reach the fancy vivid designation. When they do appear, they're treasured not just as jewelry but as natural wonders, evidence of the remarkable diversity that can emerge from a single element arranged in a single crystal structure under varying conditions. Here's something else remarkable about diamonds. Some of them fluoresce under ultraviolet light, glowing with visible light when exposed to UV radiation. Shine a UV lamp on certain diamonds, the kind of lamp sometimes used to detect counterfeit currency, and the diamond might suddenly glow blue, or sometimes yellow, green, orange, or even red. This fluorescence happens when UV light excites electrons in the diamond structure, typically at defects or impurity sites. As these electrons return to their normal state, they release energy as visible light. The effect can be subtle or dramatic. Some diamonds show no fluorescence at all. Others light up brilliantly, as if they have an internal light source. Fluorescence doesn't necessarily affect a diamond's appearance in normal lighting, though strong fluorescence can sometimes make a diamond appear slightly hazy or oily in direct sunlight. In general, though, fluorescence is just another fascinating characteristic, another variable in the complex personality of these ancient crystals, another reminder that no two diamonds are ever truly identical. The human relationship with diamonds stretches back more than 2.5 millennia, to ancient India, where diamonds were first mined from alluvial deposits. Rivers flowing from mountainous regions carried these precious stones downstream, tumbling them along riverbeds where observant people learned to recognize their distinctive appearance among ordinary pebbles. India's diamond mines, particularly those in the Golconda region, would become legendary. For more than 2,000 years, India dominated global diamond production, serving as the sole significant source of these gems for most of the ancient and medieval world. Traders carried Indian diamonds along the Silk Road, through Persia and the Middle East, eventually reaching the Mediterranean and Europe. These stones traveled thousands of miles from their riverbeds, passing through countless hands, accumulating stories and legends with each transaction. The ancient Greeks encountered these remarkable stones through trade and immediately wove them into their mythology. They believed diamonds were tears of the gods, crystallized drops of divine sorrow that had fallen to earth and solidified into indestructible gems. In another Greek legend, diamonds were said to be splinters of fallen stars, fragments of celestial light captured in physical form. These weren't mere poetic metaphors. The Greeks genuinely believed diamonds possessed supernatural origins and properties. How else could they explain a substance harder than anything else in nature, transparent yet somehow containing rainbows, seemingly eternal and unchangeable? In a world without modern geology or material science, attributing diamonds to divine or celestial sources made perfect sense. They were too extraordinary to be merely earthly. In India, where diamonds were most abundant, Hindu traditions incorporated these gems into religious practice. Ancient Hindus placed diamonds in statues of deities for protection, believing the stones possessed powerful spiritual properties that could ward off evil and bring blessings. Different diamonds were associated with different gods and goddesses. The placement of the stone, its size and quality, all carried symbolic meaning. Some traditions held that diamonds could absorb and neutralize negative energies, protecting not just the statue but the entire temple and the community it served. These weren't decorative choices. They were acts of devotion and practical magic, investments in spiritual security that drew on the diamond's perceived invincibility and purity. Warriors in various cultures believed diamonds granted courage in battle. A soldier carrying a diamond into combat, whether worn as an amulet or sewn into clothing, supposedly gained not just bravery but physical protection. The diamond's hardness translated, in the minds of ancient peoples, into an impenetrable shield. Some legends claimed that a diamond could turn aside arrows and sword blows, rendering the wearer invulnerable. While this belief seems obviously false to us now, consider the psychological effect. A warrior who truly believed himself protected by a diamond's power might fight with greater confidence and ferocity. That confidence alone could mean the difference between victory and defeat. Whether the diamond provided actual protection or simply made the warrior believe he was protected might not have mattered in practical terms. The outcome could be the same. During the Middle Ages, diamonds accumulated even more attributed powers. They were thought to have healing properties, able to cure ailments ranging from mental illness to poisoning. Medieval physicians sometimes ground diamonds into powder and administered them to patients, believing the powdered stone would absorb toxins or balance the body's humors. This practice was expensive and presumably uncomfortable, and it certainly didn't work as intended. Ingesting diamond powder has no therapeutic value and could actually cause internal damage from the sharp particles. But the belief persisted because diamonds represented purity and perfection. If something was perfect, surely it could make imperfect things, like diseased human bodies, perfect again. The logic seems strange now, but it reflects a worldview where physical properties correlated with spiritual or medical ones, where hardness implied strength that could be transferred to the sick. The very word we use for these stones reflects ancient beliefs about their nature. Diamond comes from the Greek word adamos, meaning invincible or untamable. The Greeks recognized that nothing could scratch or break a diamond through normal means. It was, from their perspective, the ultimate expression of permanence in the material world. Everything else could be worn down, dissolved, shattered. Diamonds alone seemed to resist all attempts at destruction. That sense of invincibility has clung to diamonds throughout history, shaping how we think about them even today. When we use diamonds to symbolize eternal love or unbreakable commitments, we're echoing beliefs that originated thousands of years ago, in cultures that had no understanding of crystal structures or carbon chemistry but recognized something profound in these stones nonetheless. The tradition of diamond engagement rings, so ubiquitous today that it seems timeless, actually has a specific origin point. The first documented diamond engagement ring dates to 1477, when Archduke Maximilian of Austria gave one to Mary of Burgundy. This wasn't the first engagement ring. Rings had been used to mark betrothals for centuries, but it was the first recorded instance of using a diamond specifically for this purpose. The choice was laden with symbolism. Mary of Burgundy was one of the wealthiest heiresses in Europe, and Maximilian, though an archduke, needed to impress. A diamond, rare and nearly priceless at the time, communicated not just wealth but permanence. The marriage would be as unbreakable as the stone itself, or so the symbolism suggested. Other European nobles took note. Within a generation, diamond engagement rings had become fashionable among those who could afford them, a trend that would eventually, centuries later, spread far beyond aristocracy. In medieval Europe, diamond ownership was actually restricted to nobility by law in some regions. Sumptuary laws, regulations that dictated who could wear certain fabrics, colors, or jewels, often placed diamonds in the highest category. Only monarchs and high nobility could legally own them. This wasn't just about maintaining social distinctions, though that was certainly part of it. Diamonds were so rare and valuable that they functioned almost as a form of currency or strategic resource. A collection of diamonds represented liquid wealth that could fund armies or secure alliances. Keeping them concentrated in noble hands was a way of maintaining political and economic control. Of course, these laws were sometimes ignored or circumvented. Wealthy merchants who could afford diamonds found ways to acquire them despite legal prohibitions. But the laws reflected the status diamonds held, objects so precious that their ownership itself was a privilege reserved for the elite. Fast forward to the present, and diamonds retain their special status in subtler forms. In the modern tradition of birthstones, each month associated with a particular gem, April's birthstone is the diamond. This association carries symbolic weight. Diamonds are said to symbolize purity, innocence, and eternal love, qualities that the tradition suggests are particularly relevant to those born in April. Whether there's any actual connection between birth month and these qualities is, of course, questionable. The birthstone tradition as we know it today was largely standardized in the early 20th century by jewelers associations, a commercial enterprise as much as a cultural one. But it draws on older beliefs about gemstones possessing inherent meanings and powers. For people born in April, having the diamond as their birthstone is a stroke of luck from a market value perspective. While some months are associated with relatively common and inexpensive stones, April birthdays come with the most valuable gem of all, a fact that probably brings more pride than practical benefit but reflects the diamond's continued reign as the king of gemstones in the popular imagination. In 1866, a single discovery changed the course of diamond history forever. A 15-year-old boy named Erasmus Jacobs found an unusual pebble on the banks of the Orange River in South Africa while playing. The stone, which his family used as a toy for a while, eventually caught the attention of a traveling trader who suspected it might be valuable. It was. The pebble turned out to be a 21-carat diamond, later named the Eureka diamond. News of this discovery sparked the South African diamond rush, transforming a sleepy agricultural region into the center of global diamond production almost overnight. Prospectors flooded into the area, searching riverbanks and eventually digging into the earth itself. Within a few years, South Africa would eclipse India as the world's primary source of diamonds, a position it would hold for more than a century. Just 3 years after the Eureka, another discovery accelerated this transformation. The Star of South Africa diamond, an 83-carat rough stone, was found by a shepherd who traded it for 500 sheep, 10 oxen, and a horse. When news of this magnificent diamond reached the wider world, it triggered a full-scale diamond fever. Thousands more fortune seekers descended on South Africa. Entire towns sprang up around promising dig sites. The most famous of these became Kimberley, a city that grew around what would become the Big Hole, the largest hand-dug excavation in the world. The Star of South Africa diamond itself was eventually cut into a pear-shaped gem weighing just under 48 carats, but its real value lay in what it represented, proof that South Africa contained diamonds in quantities that could satisfy global demand and create new fortunes. Global diamond mining would never be the same. What had been a trade in rare stones from limited sources became an industry, with organized mining operations, international markets, and eventually corporate control. Among all the diamonds ever found, one stands supreme in size. The Cullinan diamond remains the largest gem-quality rough diamond ever discovered. Found in 1905 at the Premier Mine in South Africa, it weighed an astounding 3,106 carats, about 1 1/3 pounds of pure diamond. The stone was so large that when first discovered, mine workers thought it might be a piece of glass, a cruel joke planted by someone. But tests confirmed its authenticity. This was a diamond of truly exceptional size and quality. The Cullinan was eventually purchased by the Transvaal government and presented to King Edward VII of England as a birthday gift. The question then became what to do with such an enormous stone. It was too large to use in a single piece of jewelry. After much deliberation, the task of cutting the Cullinan was given to Joseph Asshare, one of the world's premier diamond cutters. Asshare studied the enormous crystal for months, identifying cleavage planes and planning how to divide it. The actual moment of the first cleave was intensely dramatic. According to legend, Ashshare placed his cleaving blade against the diamond and struck it with a steel rod. The diamond split perfectly along the intended line, and Ashshare immediately fainted from the stress. Whether that detail is true or embellished, the cut was successful. The Cullinan was eventually cut into 105 stones of various sizes. The two largest pieces, Cullinan I and Cullinan II, are known as the Great Star of Africa and the Second Star of Africa. The Great Star of Africa, weighing over 530 carats in its finished form, is the largest clear-cut diamond in the world. It's set in the British sovereign's sceptre, part of the crown jewels. When you see images of British royal regalia, that enormous pear-shaped diamond in the sceptre is a piece of the Cullinan, a fragment of that incredible rough stone found in South Africa more than a century ago. Before the Cullinan, another South African diamond held the record for size. The Excelsior diamond, discovered in 1893, weighed 995 carats in the rough, nearly 1,000 carats of diamond in a single stone. For 12 years, it was the largest diamond known to exist. The Excelsior was eventually cut into 10 major gems and a number of smaller stones. The largest of these finished gems weighs just under 70 carats, beautiful but far smaller than the original rough stone. This is the eternal trade-off in diamond cutting. The cutter must remove flaws, optimize light performance, and create marketable shapes. In the process, the majority of the rough stone becomes dust. The Excelsior, though eventually surpassed in rough weight by the Cullinan, remains one of the most significant diamonds in history, a reminder that South Africa's diamond deposits were producing stones of a size and quality that the world had never seen before. Some diamonds earn their fame not from size but from history and legend. The Koh-i-Noor diamond, whose name means mountain of light in Persian, has a documented history stretching back centuries. The stone has passed through the hands of Mughal emperors, Persian Shahs, Afghan rulers, and Sikh Maharajas, often changing ownership through conquest and war. Each transfer came with bloodshed and political upheaval. Legends claim the diamond brings bad luck to male owners but good fortune to female ones, though this superstition is probably just coincidence based on the stone's history. When Britain annexed the Punjab in 1849, the Koh-i-Noor became property of the British Crown. It was presented to Queen Victoria and eventually recut to improve its brilliance, reducing it from 186 carats to just over 105. Today, the Koh-i-Noor is housed in the Tower of London, set in the crown of the Queen Mother. Its presence there remains politically controversial, with India, Pakistan, and other nations having claimed ownership at various times, arguing the diamond should be returned to its country of origin. If the Koh-i-Noor is famous for its history, the Hope diamond is famous for its color and its curse. This steel blue diamond, weighing just over 45 carats, is one of the world's most famous blue diamonds. Its color comes from trace amounts of boron, as we discussed earlier, but its fame comes from the dramatic story that follows it through history. The Hope diamond supposedly originated from a much larger blue diamond stolen from a Hindu statue in India, a theft that brought a curse upon all future owners. According to legend, the diamond has caused financial ruin, madness, and death to those who possessed it. King Louis XVI and Marie Antoinette owned it before losing their heads in the French Revolution. Later owners supposedly suffered bankruptcy, suicide, and mysterious deaths. How much of this is true and how much is embellishment is hard to say. Many of the curse stories were likely invented or exaggerated by jewelers to make the diamond seem more exotic and valuable. What's certain is that the Hope Diamond is real, spectacularly beautiful, and currently resides in the Smithsonian Institution, where millions of visitors see it each year. If there is a curse, it doesn't seem to affect museums. In the modern era, record-breaking diamonds are measured not just by size or history but by price. The pink star diamond represents the pinnacle of colored diamond value. This fancy vivid pink diamond, weighing just under 60 carats, sold at auction in 2017 for $71 million, a record-breaking price per carat that stunned even seasoned diamond dealers. Pink diamonds are exceptionally rare, and vivid pinks of significant size are almost unheard of. The pink star's color is so pure and intense that it seems to glow with internal light. Its sale price reflects not just rarity but the emergence of new wealth centers, particularly in Asia, where collectors compete for the world's finest colored diamonds. The buyer was a Hong Kong jewelry retailer, continuing a trend of Eastern buyers acquiring trophy stones at prices that would have been unimaginable just a generation ago. Size still matters, though, and in 2017, another diamond made headlines for sheer scale. The Les Eddy La Rona, a rough diamond weighing over 1,100 carats, became one of the largest rough diamonds ever found. Its name means "our light" in Swana, the language of Botswana where it was discovered. The stone was initially offered at auction with a reserve price of $70 million but failed to sell when bidding didn't reach that level. Eventually, it sold privately to a diamond manufacturer for $53 million, making it one of the most expensive rough diamonds ever sold. The Les Eddy La Rona was subsequently cut into multiple stones, the largest of which weighs over 300 carats. Like the Cullinan before it, the Les Eddy La Rona demonstrates that the Earth still occasionally yields up diamonds of truly exceptional size, stones that remind us of the geological forces that have been creating these crystals for billions of years. Not every famous diamond story has a happy ending, though. Several historic diamonds were shattered or lost during cutting, victims of miscalculation or bad luck. Diamond cutting, especially of large stones, involves calculated risks. If the cutter misreads the crystal structure or strikes along the wrong plane, a priceless diamond can split incorrectly, reducing a potential masterpiece to fragments. Some famous diamonds simply vanish from history, stolen or lost or perhaps recut beyond recognition. Others were intentionally broken into smaller pieces when demand for large single stones was low, decisions that seem tragic now but made economic sense at the time. Each lost or destroyed diamond is a reminder that these ancient stones, despite surviving for billions of years deep in the earth, can be surprisingly vulnerable once they enter human hands. We prize them for their hardness and durability, but that doesn't make them indestructible, especially when subjected to the steel blades and careful violence of the cutter's art. The global diamond industry today is dominated by just a few major producing nations. Russia and Botswana together produce over half the world's diamonds by value, their mines yielding billions of dollars worth of rough stones each year. Russia's diamond deposits, particularly in the remote Sakha Republic in Siberia, are vast and varied, producing everything from industrial-grade stones to exceptional gems. The climate there is brutal, with winter temperatures dropping to -50 degrees Celsius or colder, yet mining operations continue year-round, extracting diamonds from frozen ground. Botswana's diamond industry, meanwhile, has transformed the nation's economy since major deposits were discovered in the 1960s. The country has managed its diamond wealth relatively well, using revenues to fund education, healthcare, and infrastructure. Partnerships between the Botswanan government and mining companies have made it one of Africa's most stable and prosperous nations, a striking contrast to other diamond-producing regions where wealth has fueled conflict rather than development. For decades, one mine stood apart from all others in a very specific way. Australia's Argyle mine, located in the remote Kimberley region of Western Australia, produced most of the world's pink diamonds. More than 90% of all pink diamonds came from this single source. The mine began operations in 1983 and quickly became known not just for quantity but for producing pinks of extraordinary quality, including the occasional rare red diamond. The geology that created Argyle's pink diamonds remains somewhat mysterious. Scientists believe the color relates to structural deformations in the crystal lattice, similar to what creates red diamonds, but the specific conditions that made Argyle so productive in pink stones occurred nowhere else on Earth with the same frequency. In 2020, after nearly 4 decades of operation, Argyle closed, its economically viable deposits exhausted. The closure sent shockwaves through the colored diamond market. Pink diamond prices, already high, soared even higher as the primary source disappeared. What pink diamonds remain in the world are now finite, no longer being replenished by new production. The process of extracting diamonds from the earth is staggeringly inefficient in terms of material moved versus gems recovered. A single carat of diamond, weighing just 0.2 of a gram, requires hundreds of tons of earth to be mined, processed, and sorted. Some estimates put the figure at 250 tons or more of ore for each carat recovered. This ratio varies depending on the richness of the deposit, but even the best diamond mines involve moving enormous quantities of rock to find relatively tiny crystals. Industrial-scale diamond mining isn't like panning for gold, where you might see flakes glittering in a pan. It's more like searching for needles in a haystack the size of a mountain. Massive earth-moving equipment tears ore from open pits or underground tunnels. The ore is crushed, sorted, and processed through complex systems designed to separate diamond from surrounding rock. Most of what's extracted is waste, destined for enormous tailings piles. Diamond mining generates vast amounts of waste material, creating environmental challenges that extend far beyond the size of the mine itself. For every ton of ore that contains diamonds, dozens or hundreds of tons of overburden, the rock and soil covering the ore must first be removed and set aside. Then there's the ore that's processed but contains no diamonds, which becomes tailings. These tailings piles can be huge, artificial mountains of pulverized rock that alter landscapes and can create drainage problems if not properly managed. Some mining operations have made efforts to rehabilitate land after mining ceases, filling in pits and recontouring the earth, but the scale of disturbance in major diamond mining regions is immense. Satellite images of places like Russia's Mirny mine or South Africa's Big Hole show the sheer scope of earth that's been removed in pursuit of these crystals. The rarity of diamonds in ore becomes even more striking when you consider the actual proportions. For every million parts of rock in a typical diamond-bearing deposit, only 1 part yields a diamond. Think about that ratio. 1 in a million. If you had 1 million marbles and 1 was a diamond, you'd have to sort through all million to find it. In reality, the process is even more challenging because diamonds don't conveniently announce their presence. They're mixed with rock that may look similar, especially before being cleaned. Modern mining operations use X-ray fluorescence and other technologies to identify diamonds in crushed ore, but the fundamental challenge remains. Diamonds are vanishingly rare even in the richest deposits, and an enormous infrastructure exists solely to find and extract those few crystals from the vast quantities of ordinary rock that surround them. Once diamonds are mined and reach the market, they flow toward wealth. The United States is the world's largest diamond market, consuming more diamonds by value than any other nation. This isn't because Americans mine many diamonds themselves. U.S. diamond production is minimal. Rather, it reflects American purchasing power and cultural traditions around diamond jewelry, particularly engagement rings. The American market size and importance shapes global diamond pricing and marketing. Trends that begin in the United States often spread worldwide. When diamond companies launch marketing campaigns, they're frequently targeted at American consumers first, knowing that success in the US market often predicts success elsewhere. Within the United States, one location stands as the traditional center of the diamond trade. New York City's Diamond District, a single block of West 47th Street in Manhattan, handles a substantial portion of global diamond trade. This single city block contains hundreds of diamond and jewelry businesses, from small traders operating out of tiny offices to major international dealers. On any given day, billions of dollars worth of diamonds change hands in the Diamond District. Dealers meet in small booths, examining stones with loops, negotiating prices, and arranging trades. Much of the business operates on trust, with handshake sealing deals worth hundreds of thousands of dollars. The Diamond District's prominence has declined somewhat in recent decades as trading has globalized and moved online, but it remains a crucial node in the network that moves diamonds from mines to consumers. Walk down that block, and you're witnessing centuries of diamond trading tradition compressed into a few dozen storefronts. Yet most of the actual work of transforming rough diamonds into finished gems happens elsewhere. Surat, India processes over half of the world's rough diamonds, a remarkable concentration of cutting and polishing expertise in a single city. Thousands of small and medium-sized businesses employ hundreds of thousands of workers who spend their days examining rough stones, planning cuts, and painstakingly grinding and polishing facets. Surat's dominance in diamond processing reflects both skilled labor and economic factors. The work is labor-intensive and requires training, but not necessarily expensive equipment for smaller stones. Indian diamond processors have built a competitive advantage through generations of accumulated expertise. A rough diamond mined in Russia or Botswana might travel to Belgium or Israel for initial sorting and planning, but there's a good chance it will eventually make its way to Surat for the actual cutting and polishing before being shipped to New York, Hong Kong, or another major trading center for final sale. The United States may be the world's largest diamond consumer, but it produces very few diamonds itself. The first U.S. diamond mine of any significance opened in Arkansas, though calling it a mine might be generous. In 1806, diamonds were discovered in an area that would later become known as the Crater of Diamonds. Unlike most diamond deposits, which occur in vertical pipes that must be mined through deep excavation, the Arkansas deposit is an eroded volcanic formation where diamonds are scattered through surface soil. Various attempts at commercial mining occurred over the years, but none proved particularly profitable. The diamonds found were generally small, and the deposit wasn't rich enough to support large-scale industrial mining. In 1972, the state of Arkansas turned the site into something unique. Crater of Diamonds State Park allows public diamond hunting, the only diamond-bearing site in the world where anyone can search for diamonds and keep what they find. For a small admission fee, visitors can spend the day digging through plowed fields, searching for diamonds eroded from the underlying volcanic rock. Most people find nothing, but some get lucky. Over the years, visitors have discovered thousands of diamonds, some quite large. The largest diamond found at Crater of Diamonds was over 40 carats, discovered in 1975 by a woman who was visiting the park as a tourist. The park has become a popular destination for rockhounds and hopeful treasure hunters, a place where anyone can experience the thrill of diamond hunting without expensive equipment or expertise. Will you find anything? Probably not. But the possibility exists, and that's enough to draw thousands of visitors each year, all of them dreaming of spotting that telltale sparkle in the Arkansas dirt. For billions of years, diamonds formed only through natural geological processes deep within the Earth. That changed in 1954 when scientists at General Electric successfully created synthetic diamonds for the first time. This achievement represented decades of effort and failure. Researchers had long understood theoretically that diamond could be synthesized if you could recreate the extreme conditions of Earth's mantle, but achieving those conditions in a laboratory proved extraordinarily difficult. The GE team finally succeeded using a process that subjected carbon to immense pressure and heat in specially designed presses. The first synthetic diamonds were tiny, brown, and not particularly attractive, nothing like the gems people desired. But they were genuine diamonds, carbon atoms arranged in that characteristic crystal lattice, and they proved that humans could now create in weeks what nature required billions of years to produce. Modern technology has refined diamond synthesis into two primary methods. Lab-grown diamonds today use either HPHT, which stands for high pressure, high temperature, or chemical vapor deposition, often abbreviated as CVD. HPHT mimics nature's approach more directly, squeezing carbon under tremendous pressure while heating it to temperatures exceeding 1500 degrees Celsius. The process uses hydraulic presses capable of generating pressures of 50,000 atmospheres or more, enough to force carbon atoms into diamond's crystalline structure. CVD takes a completely different approach. Instead of crushing carbon with pressure, it grows diamond crystals from a gas. A small diamond seed is placed in a chamber filled with carbon-rich gases, typically methane. Microwaves or other energy sources break down the gas molecules, and carbon atoms settle onto the seed, slowly building up layer by layer into a larger diamond crystal. Both methods work, and both produce genuine diamonds, though each has advantages for different applications. The speed of laboratory diamond growth would astonish nature. A lab-grown diamond can form in about 1 month, sometimes less depending on desired size. Compare that to the millions or billions of years required for natural diamonds, and the difference seems almost miraculous. Of course, the month-long process requires constant energy input and carefully controlled conditions, but still, a month versus a billion years represents an impressive acceleration. This speed means that lab-grown diamond production can respond quickly to demand. If the market needs more diamonds, manufacturers can simply grow more, limited only by their equipment capacity and energy costs. Natural diamond supply, conversely, depends on discovering and developing new mines, a process that can take decades from initial exploration to production. Here's the crucial fact that often surprises people: lab-grown diamonds are chemically identical to natural diamonds. They're not imitations or simulants like cubic zirconia or moissanite, which are different materials that merely resemble diamonds. Lab-grown diamonds are real diamonds, carbon atoms arranged in the same crystal structure. Under a microscope or spectrometer, lab-grown and natural diamonds show the same physical and optical properties. They have the same hardness, the same refractive index, the same thermal conductivity. If you handed a gemologist a collection of diamonds and asked which were natural and which were lab-grown, they couldn't tell you just by looking. They'd need specialized equipment to detect subtle differences in trace elements or growth patterns, tiny clues that reveal a diamond's origin but don't affect its essential nature as diamond. This chemical identity raises interesting questions about value. Lab-grown diamonds typically cost significantly less than mined diamonds of equivalent size and quality, sometimes 30 to 50% less or even more depending on current market conditions. This price difference doesn't reflect any difference in the diamond itself. It reflects supply and scarcity. Natural diamonds are rare, limited by what nature has produced and what humans can find. Lab-grown diamonds are limited only by manufacturing capacity, which can expand with investment. Some argue that natural diamonds deserve their premium because of their age and natural origin, the romance of a stone that formed billions of years ago versus one created last month in a factory. Others see lab-grown diamonds as a more ethical and environmentally friendly choice, avoiding the environmental and sometimes human costs of mining. The market is still adjusting to this new reality, trying to find equilibrium between natural and synthetic stones. The jewelry industry initially resisted lab-grown diamonds, fearing they would undermine the natural diamond market. For years, major diamond companies insisted that lab-grown stones should be called something other than diamonds and should be clearly distinguished from natural stones. But reality and regulation have moved toward acceptance. Regulatory bodies now treat lab and natural diamonds equally in most respects, requiring only that lab-grown stones be disclosed as such to consumers. The Federal Trade Commission in the United States and similar bodies elsewhere have ruled that lab-grown diamonds can be called diamonds without qualification, though sellers must inform buyers about their origin. This represents a significant shift in industry thinking, an acknowledgement that a diamond is a diamond regardless of whether it formed in the earth or in a laboratory. While gemstone applications get the most attention, most synthetic diamonds serve industrial purposes. Synthetic diamonds power cutting tools and electronics, applications where diamond's hardness and other properties matter more than its appearance. Diamond-tipped saw blades can cut through concrete, asphalt, and stone. Diamond drill bits can bore through the hardest rock formations. Diamond grinding wheels can shape and polish other materials with precision impossible using softer abrasives. The industrial diamond market actually dwarfs the gem market in terms of volume. Millions of carats of synthetic diamonds are produced each year for industrial use, most of them small, low-quality crystals or even diamond powder that would never be considered for jewelry but perform admirably in cutting and grinding applications. The medical field has found increasingly sophisticated uses for diamond. Diamonds are used in high-precision medical instruments, particularly in surgical tools where extreme sharpness and durability matter. Diamond-coated scalpels can make cleaner incisions than traditional steel blades, and they maintain their edge longer. Diamond-tipped instruments are used in eye surgery, where precision is measured in micrometers. The same hardness that makes diamonds useful for cutting rock makes them ideal for cutting or abrading human tissue when necessary, and unlike metal instruments, diamond doesn't corrode or degrade in biological environments. Even more remarkably, diamonds are biocompatible for implants and joint replacements. The human body generally tolerates diamond without triggering immune reactions or rejection. Researchers have explored coating medical implants with diamond or diamond-like carbon to improve their performance and longevity. A hip or knee replacement coated with diamond could potentially last longer and cause less wear on surrounding tissue than conventional metal or ceramic components. The coating's hardness reduces friction and debris generation, common problems in joint replacements that can lead to inflammation and eventual implant failure. While diamond-coated implants are still relatively rare and expensive, they represent a growing field of medical technology where diamonds' unique properties offer solutions to persistent challenges. Beyond Earth, diamonds serve in extreme environments such as space probes and satellites. Diamonds' ability to withstand intense radiation, extreme temperatures, and the vacuum of space makes it useful in aerospace applications. Diamond windows can protect sensitive instruments from radiation while allowing light to pass through for observation or communication. Diamond heat sinks can manage the thermal loads in electronic systems operating in space, where conventional cooling methods don't work. Some researchers have proposed using diamond in components for future missions to Venus, where surface temperatures exceed 450 degrees Celsius, hot enough to melt lead. Diamond's thermal stability and strength could enable instruments to survive conditions that would destroy other materials. From the depths of Earth's mantle to the surface of distant planets, from jewelry boxes to operating rooms to spacecraft, diamond has found its way into an extraordinary range of applications, each exploiting the remarkable properties that emerge from carbon atoms arranged in that simple yet extraordinary crystalline lattice. Light and diamond interact in fascinating ways that extend beyond the sparkle we admire in jewelry. Diamonds absorb infrared light poorly, which makes them ideal for laser windows in high-power systems. When you need to transmit a powerful laser beam from one place to another, you need a window material that won't absorb the energy and heat up. Most materials will absorb at least some infrared radiation, converting that energy to heat and potentially cracking or melting under intense laser exposure. Diamond, however, is remarkably transparent to infrared wavelengths. A laser beam can pass through a diamond window with minimal energy loss, and the diamond itself remains cool even when handling kilowatts of power. This property makes diamond essential in industrial laser cutting systems, scientific research equipment, and military applications where high-power lasers need robust, reliable optical components. Not all diamonds form through the slow geological processes we've been discussing. Nanodiamonds, diamond crystals so small they're measured in nanometers, thousands of times smaller than the width of a human hair, form during meteorite impacts. When a large asteroid or comet strikes Earth or another planetary body, the impact generates pressures and temperatures that can instantly convert carbon-bearing materials into diamond. These diamonds don't have time to grow large. The extreme conditions exist for only microseconds or milliseconds, just long enough to create tiny crystalline structures before the pressure wave passes and conditions return to normal. Scientists have found nanodiamonds in meteorites themselves, in impact crater sites, and even in sedimentary layers associated with ancient impact events. The layer of sediment marking the extinction of the dinosaurs 66 million years ago contains nanodiamonds, tiny testament to the violence of the asteroid impact that changed Earth's climate and killed 3/4 of all species. These nanodiamonds aren't just geological curiosities. Nanodiamonds are used in lubricants and biomedical research, applications that exploit their tiny size and diamond properties in useful ways. In lubricants, nanodiamonds act as microscopic ball bearings, reducing friction between moving parts. They're so small they can fit into the tiny gaps between metal surfaces in engines or machinery, providing lubrication at scales where conventional oil molecules are too large to be effective. The nanodiamonds are hard enough that they don't get crushed under pressure, and they can significantly reduce wear in high-stress applications. In biomedical research, nanodiamonds serve as delivery vehicles for drugs or as fluorescent markers for tracking biological processes. Their biocompatibility, combined with their ability to be functionalized with various molecules attached to their surfaces, makes them versatile tools. Researchers can attach cancer drugs to nanodiamonds and potentially target tumors more precisely, or they can use fluorescent nanodiamonds to track how cells move and interact. At even smaller scales, diamonds reveal quantum properties that scientists are only beginning to exploit. Certain defects in diamonds' crystal structure, particularly what are called nitrogen vacancy centers, enable quantum computing applications. A nitrogen vacancy center occurs when a nitrogen atom replaces a carbon atom in the lattice, and an adjacent position is vacant, missing its carbon atom entirely. This defect creates a tiny quantum system that can be manipulated with lasers and microwaves. The remarkable thing is that these defects work at room temperature, unlike most quantum systems which require cooling to near absolute zero. Scientists can use nitrogen vacancy centers to store and process quantum information, creating what might eventually become quantum computers. The field is still in early stages, but diamond-based quantum systems have demonstrated basic quantum operations and could potentially scale to more complex computing tasks. These same nitrogen vacancy centers also enable ultra-sensitive magnetic field detection. The quantum state of the defect is exquisitely sensitive to magnetic fields, changing in measurable ways when exposed to even tiny magnetic variations. By monitoring how a nitrogen vacancy center responds, scientists can detect magnetic fields far weaker than what conventional sensors can measure. This capability has applications ranging from reading data on hard drives to mapping neural activity in the brain. Neurons generate small magnetic fields when they fire, and diamond sensors could potentially detect these fields with enough precision to create detailed maps of brain activity without requiring surgery or bulky equipment like MRI machines. More broadly, diamonds support emerging quantum sensing technologies that go beyond magnetic fields. Quantum sensors using diamond can detect temperature changes, pressure variations, and even individual molecules based on how these factors affect the quantum states of defects in the diamond lattice. These sensors could revolutionize fields from medical diagnostics to materials science. Imagine a diamond chip that could detect a single cancer cell in a blood sample, or measure the stress in a bridge component before any visible crack appears. The technology is still developing, but the fundamental physics works, and researchers worldwide are racing to turn laboratory demonstrations into practical devices. Here's something that might surprise you about diamonds' ubiquity. Diamonds appear as nanoparticles in candle flames, tiny diamond crystals forming and disappearing in the brief moment before the carbon atoms combine with oxygen and vanish as carbon dioxide. Scientists discovered this phenomenon only recently using sophisticated analytical techniques. In the inner part of a candle flame, where combustion isn't complete and the temperature is relatively low, carbon atoms from the vaporized wax can briefly assemble into diamond structure before being swept upward into hotter regions where they combust. These flame diamonds are incredibly short-lived and impossibly small, but they demonstrate something profound about diamond formation. The fact that carbon atoms can assemble into diamond even in combustion, even in a simple candle flame, shows that diamond formation doesn't necessarily require the extreme conditions of Earth's mantle. It needs the right local environment, even if only for an instant. The same carbon atom could be part of the wax in a candle, become a nanodiamond in the flame, and then become carbon dioxide in the air, all within seconds. The carbon doesn't fundamentally change. What changes is how it's arranged with other carbon atoms, and that arrangement determines everything about its properties. This brings us back to a fundamental truth about carbon and diamond. Graphite and diamonds differ only in atomic arrangement. Both are pure carbon, nothing added, nothing removed. In graphite, carbon atoms form flat sheets where each atom bonds to 3 neighbors in a hexagonal pattern. These sheets stack loosely on top of each other, held together by weak forces. The result is a soft, slippery material that conducts electricity and leaves marks on paper. In diamond, each carbon atom bonds to 4 neighbors in a 3-dimensional tetrahedral pattern, creating that rigid cubic lattice we've discussed. The result is the hardest natural material, electrically insulating and brilliantly transparent. Same atoms, completely different properties, all because of arrangement. This principle extends beyond just diamond and graphite. Structure, not composition, defines diamond's properties and indeed defines the properties of all materials. Chemistry tells us what atoms are present, but materials science tells us how those atoms are arranged, and the arrangement matters more than the identity of the atoms in determining how a material behaves. Silicon and carbon are neighbors on the periodic table with similar chemistry, but diamond and silicon have completely different properties because their atoms arrange differently. Even within carbon itself, we have diamond, graphite, fullerenes which are soccer ball-shaped molecules, carbon nanotubes which are rolled-up sheets of graphite, and other forms, all pure carbon, all with radically different properties. The lesson is profound and applies throughout nature. Structure matters. How things are put together determines what they can do. A diamond is remarkable not because carbon is remarkable, though carbon is a fascinating element, but because of how carbon atoms are arranged in diamond. That arrangement, that structure, is what gives diamond its hardness, its brilliance, its thermal conductivity, its chemical stability, all the properties that have made it precious to humans and useful in countless applications. The diamond is the structure, and the structure is the diamond. When we look up at the night sky, we're looking at a universe filled with carbon. It's one of the most common elements in the cosmos, forged in the hearts of dying stars and scattered through space when those stars explode. Given how abundant carbon is, and given the extreme conditions that exist throughout the universe, astronomers believe some exoplanets may be rich in diamond. These wouldn't be planets with diamond deposits like Earth. They would be worlds where diamond makes up a substantial portion of the planetary mass. The theory suggests that in certain star systems, particularly around stars with unusual chemical compositions, planets could form from carbon-rich material rather than the silicon and oxygen-rich material that dominates Earth. Under the right conditions of pressure and temperature, much of that carbon could crystallize into diamond, creating worlds where the ground beneath your feet, if you could somehow stand there, would be diamond bedrock kilometers thick. This isn't pure speculation. Astronomers have actually identified candidate planets that might fit this description. One known planet, called 55 Cancri E, may be composed largely of diamond. This super-Earth orbits a star about 40 light-years away, so close to its sun that its surface temperature reaches thousands of degrees. Observations of the planet's mass and radius, combined with models of its parent star's chemistry, suggest it could contain enormous amounts of carbon. Some estimates propose that up to a third of the planet's mass might be diamond, a mantle of crystallized carbon surrounding a dense iron core. We can't visit 55 Cancri E to confirm this, and uncertainties remain in the models, But if the estimates are correct, this single planet contains more diamond than exists in all of Earth by factors of trillions. It's a humbling thought. All the diamonds ever mined on Earth, all the legendary stones we've discussed, would be insignificant compared to even a tiny fraction of one diamond planet. Planets aren't the only cosmic diamonds. When certain stars die, they leave behind remnants that are essentially giant diamonds floating in space. A massive white dwarf star, the collapsed core of a star that has burned through its nuclear fuel, can crystallize as it cools. White dwarfs are incredibly dense, packing a star's worth of material into a sphere about the size of Earth. As they radiate away their heat over billions of years, the carbon and oxygen in their interiors can solidify into a crystalline structure. The result is effectively a cosmic diamond, a stellar core that has become a single enormous crystal. One such star, catalogued as BPM 37093 and nicknamed Lucy after the Beatles song Lucy in the Sky with Diamonds, is thought to be a crystallized white dwarf about 50 light-years from Earth. The scale of this stellar diamond defies comprehension. This stellar diamond weighs trillions of carats, a number so large it loses meaning. If you could somehow cut this star into 1-carat gems, you'd have enough diamonds to give every person who has ever lived on Earth trillions of stones each, and you'd still have barely made a dent in the star's mass. Of course, you can't cut a white dwarf. The gravity alone would crush anything that tried to approach, and the temperatures, though cooling, remain higher than anything we could withstand. But the fact that such objects exist, that nature can create diamond on stellar scales, reminds us that Earth's diamonds, for all their value and beauty here, represent just the tiniest fraction of the diamond that exists in the universe. These discoveries confirm that diamonds exist beyond Earth in space environments, not as rarities but potentially as common components of certain planetary and stellar systems. Meteorites have brought us samples of extraterrestrial diamonds, tiny crystals formed in asteroid impacts or perhaps in the protoplanetary disk that gave birth to our solar system. Future space missions might bring back more exotic samples. Some scientists have proposed that gas giant planets like Jupiter and Saturn might produce diamond rain, where carbon compounds in the atmosphere are compressed by the immense atmospheric pressure until they crystallize and fall toward the planet's core as diamond hailstones. The universe, it seems, finds countless ways to arrange carbon atoms into diamond structure, from candle flames to the interiors of stars. Back on Earth, scientists continue to search for materials that might challenge diamond supremacy. Some materials may surpass diamond in hardness under special conditions. Researchers have created substances with exotic names like aggregated carbon nanorods and wurtzite boron nitride that show hardness approaching or potentially exceeding diamond in specific crystallographic directions or under particular testing conditions. The challenge is that hardness itself is complex to define and measure. Different tests give different results, and a material might be harder than diamond in one direction but softer in another. Still, the quest continues, driven partly by scientific curiosity and partly by practical considerations. A material harder than diamond would have immediate applications in cutting tools and wear-resistant coatings. New ultra-hard materials continue to be studied in laboratories worldwide. Scientists experiment with different elements, different structures, and different synthesis methods, trying to find combinations that might push beyond diamond's limits. Some researchers are exploring how adding small amounts of other elements to diamond might enhance its properties. Others are creating entirely new materials with structures inspired by diamond but built from different atoms. It's painstaking work that requires sophisticated equipment and deep understanding of material science, but progress continues. Each new discovery teaches us more about how atomic arrangement creates properties, knowledge that extends far beyond just finding something harder than diamond. Yet despite all this research, diamond remains the benchmark for hardness. When scientists create a new material and want to characterize its hardness, they test it against diamond. When engineers need the hardest tool available for a practical application, they still turn to diamond more often than not. Diamond's combination of properties, not just hardness but also thermal conductivity, chemical stability, and optical characteristics, makes it uniquely valuable. Even if something harder is discovered, diamond will retain importance because hardness is just one of many factors that make it useful. The story of diamond demonstrates how its unique properties bridge geology, industry, and technology. Diamonds connect the deep earth to the cosmos, link ancient history to cutting-edge science, tie together aesthetics and engineering. Few materials span such breadth. A diamond engagement ring and a diamond-tipped industrial drill bit have nothing in common in terms of purpose or value, yet they both exist because carbon atoms can lock into that particular crystalline arrangement. Diamond has shaped human culture, influenced economics, driven exploration, and enabled technologies. It has inspired romance and financed wars, adorned royalty and carved granite, measured geological time, and might someday process quantum information. When you consider everything we've discussed, from formation billions of years ago deep in Earth's mantle, through violent volcanic eruptions that brought crystals to the surface, through human discovery and the development of cutting techniques, through modern synthesis and industrial applications, through quantum computing and cosmic diamonds in distant star systems, one conclusion becomes inescapable. Diamonds remain one of nature's most extraordinary materials, a substance that continues to surprise and inspire even after thousands of years of human fascination. They are ancient and modern, natural and synthetic, ornamental and industrial, earthly and cosmic. They are, in the end, just carbon, the same element that makes up the graphite in pencils and the carbon dioxide we exhale. But arranged in that particular way, bonded in that specific structure, carbon becomes diamond, and diamond becomes something that captures human imagination like few other substances can. As you drift towards sleep, consider that the universe is still making diamonds, right now, in Earth's mantle, in laboratory chambers, in the atmospheres of distant planets, in the cooling cores of dead stars. The process that began billions of years ago continues, and diamonds, those crystallized moments of deep time and extreme conditions, remain one of the most remarkable outcomes of the fundamental forces that shape matter throughout the cosmos.